Welcome to Lesson 12, where we will be looking at applications of arithmetic with powers of 10. We'll be using powers of 10 to help us make calculations with large and small numbers. To be successful in this video, you'll be able to apply what you've already learned about powers of 10 to answer questions about real-world situations. We start off with the warm-up, what information do you need? You're given two questions. Pause here and think about what information is needed in order to answer these questions. Question 1 talks about how many meter sticks does it take to equal the mass of the moon? You would need to know the mass of the moon and the mass of a meter stick in order to answer this question. Question 2 says if all of these meter sticks were lined up end to end, would they reach the moon? You would have to know the distance to the moon in order to answer that question. As we move into the second activity, meter sticks to the moon, I'm going to actually give you some of the information that is needed in order to answer some of the questions that are in this activity. So here's what you would need. The mass of an average classroom meter stick is roughly 0.2 kilograms. The length of an average classroom meter stick is 1 meter. The mass of the moon is approximately 7 times 10 to the 22nd power kilograms. And the moon is roughly 3.8 times 10 to the 8 meters away from Earth. You might want to pause here and leave this information on your screen or write it down before moving on. Otherwise, you're going to completely pause the video so that way you could answer questions 1 to 4 before we discuss together. Okay, so question 1 asks, how many meter sticks does it take to equal the mass of the moon? So we know that the mass of a meter stick is 0.22 kilograms. We're going to go ahead and write that as 2 times 10 to the negative first power for a reason you'll see in a second why. We also know that the mass of the moon is 7 times 10 to the 22nd kilograms. So with that information, we're going to go ahead and divide the mass of the moon by the mass of the meter stick. And that's why I rewrote that to 2 times 10 to the negative first, so that way we can apply our exponent rules here and divide. So we know 7 divided by 2 is 3.5, and 10 to the 22nd over 10 to the negative first, you're subtracting those exponents, so you get 10 to the 23rd, and that represents the number of meter sticks it takes to equal the mass of the moon. Part 2 asks you to label the number line and plot your answer for the number of meter sticks. So we're taking that 3.5 times 10 to the 23rd, plotting that on our number line. So we need to first label our number line. So we're going to actually break up 10 to the 24th into 10 equal parts, where each part is being multiplied by 10 to the 23rd power, which allows us to go ahead and plot the 3.5 times 10 to the 23rd on that number line. So it should look like this. In question 3, if you took all the meter sticks from the last question, which was that 3.5 that we just plotted, and line them up end to end, will they reach the moon? Will they reach beyond the moon? And if yes, how many times farther will they reach? So we have that 3.5 times 10 to the 23rd meter sticks. We also know that it is 3.8 times 10 to the 8th power meters from Earth to moon. So we're actually going to go ahead and rewrite this to say that the number of meter sticks is actually close to 4 times 10 to the 23rd meters. And we're also going to rewrite this to say that this is approximately 4 times 10 to the 8th meters. And this is just going to allow us to make a quick estimate here. So because those first factors are the same, we really can just look at the powers of 10, 10 to the 23rd and 10 to the 8th. And we can see that this is approximately 10 to the 15 times more than the 10 to the 8th. The 10 to the 23rd is, there we go, is 15 times farther. So yes, they will reach beyond the moon because of that reasoning. So 1 light year is approximately 10 to the 16th meters. How many light years away would the meter sticks reach? So let's write what we know already. So we know 1 light year is approximately this many meters. And we're essentially trying to figure out how many light years it's going to be to equal that 3.5 times 10 to the 23rd meters. So in order to determine that, we're actually going to go ahead and divide the 3.5 times 10 to the 23rd meters by the 10 to the 16th. And I just rewrote that with a factor of 1 in front of it just for a visual for you guys. So when we go ahead and divide that, we're going to see that it's 3.5 times 10 to the 7 light years. Now that you have that information, we'll go ahead and plot that on the number line. So we know that we're going to have to divide 10 to the 8 in 10 equal parts. Oops, there's a typo there. That should say 10 to the 8th. So ignore that last 7. It should say 10 to the 8th as the very last tick mark and 10 to the 7th for everything else. So we would go ahead and plot that in the middle there of the 3 and the 4 times 10 to the 7th, and that would represent the number of light years. So to solve the problems in this lesson, you had to determine what information was needed. Did you find that to be fairly straightforward or challenging? And what made it straightforward or challenging? So that's just something to kind of reflect on here. How did exponent rules and powers of 10 make the calculations easier? Powers of 10 make the numbers easier to express and interpret. So again, if you're just first conceptually thinking about what is happening in these real world situations, what operations do I need to use in order to answer the question, and then really just applying those rules. The rules of exponents are handy for comparing how many times as large or as small one number is to another. Would an estimate be an acceptable answer for problems like these? It just depends on the questions and how the answers would be used. So if the answers are for comparison or just general information, estimates are very adequate in these types of situations. So it just kind of all depends on what the question's asking. Read through the lesson summary if you choose. Otherwise, you are successful at this video if you're able to apply what you learned about powers of 10 from previous videos and are able to answer real-world questions.